Hi folks, I posted a small script on the website that walks you through the bivariate normal simulation problem from Homework 8, where you're trying to decide what the right mix of stocks and bonds is in a simple asset allocation problem. So you'll need a few libraries and helper scripts for this one. Obviously you need the Mosaic library and then the library we installed last week called mvtnorm. Go ahead and load those. And then you'll also need this helper function rbvnorm.r, which you can either source directly from my website like this, or you could even go download this file if you wanted to have it available offline, and then every time just open and copy and paste the function that's in that straight to the console. So now we've got the libraries loaded and the helper function available for use. Let's go ahead and put our assumptions about the mean, standard deviation, and correlation of the assets here. So these are the numbers that we were working with. 6.5% average return net of inflation for stocks, 1.5% for bonds, 20% standard deviation for stocks, 10% for bonds, and a correlation of minus 10%. So these are obviously assumptions. They're based loosely on past data, but the way to think about what we're doing here is building a scenario. Imagine that the returns and volatilities and covariance of stocks and bonds followed a particular set of assumptions. What would our optimal portfolio decision look like? So let's go ahead and put those into memory here. Now let's look at the simplest way. And if you remember, our routine for simulating from the bivariate normal was like this. We called RBV norm with the number of samples that we want and the corresponding parameters of the distribution. There is what our correlation structure of stocks and bonds look like. If we want to know what the expected long-term growth rate of these different portfolios are, so there's a 50-50 split, an 80-20 split in favor of stocks, and then the all-stock portfolio. The simplest way to do it is to appeal to the result that we discussed in class. So going back to the homework, remember following our discussion in class that maximizing the growth rate is equivalent to maximizing this expected value right here. So y sub t is the per period return on your investment in any given year. We want to take the expected value of log of 1 plus yt, and if we maximize this, then we will maximize our portfolio's long-term growth rate. So let's put that into practice using Monte Carlo simulation. So here I'm going to simulate 10,000 sets of returns, and this is not actually building a portfolio that grows over time. I'm just calculating that expected value purely by Monte Carlo simulation. So every time I pass through the do loop here, and I'm doing these 10,000 times, I simulate a set of returns from the bivariate normal, just one. Okay, so if I execute line 25 there, what do I get? In this particular simulation, I got up 2.3% for stocks and down minus 8% for bonds. All right, what about the portfolio return? Well, my portfolio return, if I have an equally weighted balance of assets in each of those two, holdings in each of those two assets, is just a 50-50 average of the returns in stocks right here and the returns in bonds right here. Okay, so my composite portfolio return, equally weighted in both set of assets here, is minus 3.2%. And so now what I want to return from the do loop is the log of the portfolio return, because this is the thing whose expected value we want. So the logic of this do loop here is let's simulate 10,000 examples of the log of 1 plus our composite return. And let's go ahead and let this run in the background. It takes a little bit. Once we've simulated 10,000 of those, we can calculate their mean. And here the mean of that log of 1 plus yt, where y here is portfolio return, is about 0.34. And we can do the same thing again for the 80-20 split of stocks and bonds. And we get a slightly higher number. And then we can do the same thing for the 100-0 split of stocks and bonds. And you'll see here that we actually get the highest number of all. And it's only a little bit higher. One thing you'd probably want to check is if you do this again, there's some Monte Carlo variability here. You either do this again, 10,000 different samples of each one, or maybe even a larger sample size, 100,000 Monte Carlo samples, that this relative ordering is stable, that portfolio 1 always has the lowest expected value of log of 1 plus yt, portfolio 2 is in the middle, and portfolio 3, the 100% stocks, has the highest long-term growth rate. Okay, so that's probably the simplest way to do it, and if you actually wanted to back out what the implied growth rate was, we've derived a formula in class that says if you take the mean, or the expected value of log of 1 plus yt, and you plug it into this formula right here, e to that number minus 1, you get the implied growth rate of the portfolio. So it looks like the implied growth rate of the 50-50 split is about 3.5% per year, of the 80-20 split is about 4.2% per year, and of the 100% stocks, it's about 4.6% per year. Okay, so that's probably the most straightforward way, at least the way that involves the least amount of code. Here's an alternate way. And I'm only going to do a low Monte Carlo simulation here because this takes a little bit of time to run. The alternate way to do this is just to simulate the growth of a dollar over time for a very, very long horizon. So I'm picking 100 years as my horizon right here. And then we just see who's wealthier at the end of 100 years. And that's a pretty good approximation to the long-term growth rate as well. All right, so let's pick a horizon of 100, and let's look at what I'm doing here inside the do loop. I'll just simulate the growth of a dollar of investment. Doesn't matter how much my initial wealth is, so my total wealth starts out as a dollar. And here I'll simulate the 50-50 split, although you can modify this script to do whatever split you want. So I've got my portfolio weights is 0.5, 0.5, that vector right there, which means that my holdings are a measly 50 cents in each of stocks and bonds right here. And now let's use the basic template for a for loop that we've got. We're going to loop from 1 up to our horizon, which in this case is 100 years. Every time we're going to simulate a single return from the bivariate normal distribution with the given parameters. We will update our holdings. Okay, so now after a single year in this simulation, we ended up with 58 cents of stocks and 54 cents of bonds, a good year. Then we sum our holdings and rebalance our portfolio so that our total wealth is now equally distributed among the two assets. So if you do this once, right here, at the end of 100 years, it looks like my $1 is turned into $40. Again, now it's $12, $40, $20, and so forth. So if we do this 250 times, and every time simulating a 100-year investment trajectory, you can see why I'm only doing 250, because it does take a while here. To just do one takes a little bit, to do 250 takes a little bit longer. If I want to do enough, I probably need to do 10,000 of these and let it run over lunch or something like that. In any event, there's oops, I got it wrong here. It's not port 1, it's sim 1 right there. So mean of sim $1 result. And it looks like my mean wealth at the end of 100 years here is about $50. So then you'd want to repeat this exercise with a much bigger Monte Carlo sample size and for the different combinations of portfolio weights, 50-50, 80-20, and 1-0. And then you'll be able to compare the terminal wealth, which is a pretty good proxy for the long-term growth rate of the two portfolios.